Welcome everyone to Computer Programming course for Chemical Engineering. This is part of undergraduate course at Chemical Engineering, Faculty of Engineering, Universitas Gadjah Mada in Indonesia. In this exercise, we are going to demonstrate how to solve numerical integration using Simpson one-third rule method. And we are going to use Python for this exercise. So Simpson one-third rule is a common formula that we use in order to solve numerical integrations. So this method has better accuracy compared to trapezoidal rule. So this is how it looks like, the general formula. If you have fx dx integration from a to b, you divide the a from a to b into a number of points, and then you discretize, and then you evaluate the fx value for each points. So the number of discretization points should be an even number, or in other words, the total number of points is an odd number. So again, this is illustration for Simpson rule. We have a number of points. This is I equal to 0, I equal to 1, and then finally we have I equal to n. For each point, we evaluate the value of fx, and then from this fx, we can multiply the odd position by 4, the even position by 2, and then you sum them all and multiply with b minus a over 3n. So I'm not going to focus on the numerical method of Simpson. I'm just going to demonstrate how to use Simpson formula to solve an integration problem that we face in chemical engineering. So in this exercise, we will solve a reactor design for heterogeneous reactions. So here we have a catalytic reactions which reacts A becomes B in gas phase. It is carried out in a circulating fluidized bed reactor. And the reaction rate here, it follows Langmuir-Hinshelwood mechanism. For this reaction rate, we have numerator of K1 multiplied by Ca, and then the denominator is 1 plus K2 Ca plus K3 times Cb. And Ca and Cb are concentrations of component A and B. And once we have the reaction rate, we can estimate the volume of reactor, or in other words, in this case is the height of the reactor. And by setting up mass balance for plug flow reactor, we can obtain following formula where the height of reactors is basically equal to Ca0 multiplied by U and integration of 1 over minus Ra multiplied by dx. And this integration should operate from 0 to x. So x is the final conversion that you would expect. And then for this reaction rate, we can substitute Ca and Cb as a function of conversions as follows. And in this exercise, for calculation data, we have been provided with Ca0, Cb0, U, K1, K2, and K3. So the output of this demonstration, we are going to make a table and a graph which shows the height of the reactor as a function of conversion. And the conversion should operate from 0 up to 0.9. So we will demonstrate this exercise in Python. So we will use Spyder as Python environment, and this is how Spyder looks like. So basically it has a editor window, so editor, the place where we will write all our programs, main program, subroutine, we will write it here. And then this is the variable explorer or file explorer, and then we will have console. This is something like a command window in MATLAB. So back to this exercise, in order to calculate the height of the reactor, so we can make a program structure as follows. So we will divide our program into 3 parts. And the first part, I will call it as a main program. This is the place where we provide the data, and then for calculation process to call the all subroutines, and plotting and preparing table. And in order to run this main program, we need to create a subroutine. This is subroutine which contains Simpson programs. And it should be noted that in order to run this subroutine, we need to have input of x final. What is the x final that you expect? And as a result, you will get integration results. And in order to run Simpson program, we need to create another subroutine. We call it a function, and this is we call it y. The input is x. What is the conversion? And then the output is y. We call it y as 1 over RA. This is 1 over the reaction rates. So when you run this over and over, you will get integration result for each value of x final. And once you receive the integration result, you need to put it in a vector. I illustrate this as a book shelf. And for instance, if you receive integration result for xf1, the final conversion 1, you put it in the top place here. And then similarly, when you get the integration result xf2, you put it below lower shelf, and so on until you reach the bottom of your vector. So finally, once you obtain this container, you can make it as a table. You can present this as a table or as a plot. It is also important to mention that this kind of structure, I would say this is the best practice, how you create a nice and clean program in Python. I don't say that this is the only way to solve for this problem, but I would say from my experience, this kind of structure is good, in order to allow you to give you flexibility if you want to change your program later on, and then if you want to debug if there is any problem with your program, with your large program, and then it is easy for you to fix and find error. And also later on, this kind of structure is also important when you have a larger program. Later on, we will encounter such case in this course. Okay, again, so I will demonstrate here how to create subroutine number 3 or part number 3, 2, and 1. So keep this structure or architect in your mind, because we will back and forth to see this kind of structure. Okay, now I'm going to show you we go back to Spyder environment, and in Spyder how we implement subroutine 3 to 1, our main program. We usually begin our coding with import library. This is standard in Python, where we import NumPy or plotting. And yes, matplotlib is the library for plotting. So this will help us later on if we want to present our results in a nice way. Okay, the structure, as I said earlier, it will consist of main program and then subroutine. But the way we create in Spyder is a little bit different. So the place here is we place it for data, what data that you have from your problems, and then instead of making main program right away, we make a subroutine 1, we make subroutine 2, and so on. So if you have subroutine that you plan to construct, you make it after data, after you declare your data. Okay, so this is the place for subroutine. And then finally, this is main program. This is the place or the command to call all the subroutine. So this is the place where you control the beginning of your program, and then how you get the output, the final output of your program. So this is control in main program. And usually once you get the results here, you want to do a plotting. So after that, it can be plotting or preparing table. Okay, So keep this in mind. This is the standard structure of programming in Python. Okay, for this exercise, we will start with making data. We provide all the information that we have from the problem. So if you look at the PowerPoint, we have this information: CB0 is equal to 0, and then U 7.5, K1 is equal to 8, K2 is equal to 3, and then K3 is equal to 0.01. So check again if you make any typo here. Okay, 0.2, 0, 7.5, 8, 3, 0.01. It seems like it's correct. And then like how many results or X final that you want to create from this exercise. Let's say NZ is equal to 21. I will come back why this is I decided by myself. It's up to you. And then the integration step, how many intervals that you would like to have in your integration later on. So I put this 88. This should be an even number. Okay. So basically, this is the basic informations. The conversions, initial conversion is 0. So I put this XXA is 0, just a small case. So after you provide all this information, you can run it actually. Run it, and then you can put your Simpson exercise version number 2. Okay, you can run this program, and you will see in your variable explorer, you can check the value. It is stored there, and in NZ, K1, K2, and so on. So if you, just in case you need to do a small practice, what is the value of n in, you can type it here, and it will give you results of 88. So that's just for small exercise. Okay, after we create data, and then as I mentioned earlier, we would like to create subroutine. So I decided to make a subroutine or part number 3 first. So this is a subroutine which receives input of conversion and output as y. In this case, y again is 1 over RA. So in order to make subroutine, you start with def. So I call it as reaction rate. It receives input as x. So what happened here, when you receive conversions, every time you receive conversion, you can calculate CA, right? CA is equal to CA 0 multiply 1 minus x. And then similarly, CB is CB 0 multiply 1 plus x. So when you have CB and CA, you can calculate the RA, which is K1 times CA over 1 plus K2 times CA plus K3 times CB. I have to double check again with the problems that we have here. K1 CA, 1 plus K2 CA, K3 CB. It seems like it is correct. And then we define what we call as y, 1 over RA. So that's the return or the output that we expect from this subroutine. So return y. Okay, so basically we are done with part number 3. We check again that RA K1 CA over 1 plus K2 CA plus K3 CB. It is important to mention that even if you type your subroutine quite up here just after data, it will not be executed. It won't be executed. If you run this, so you get nothing. You don't get any y here, because in order to call this subroutine, what you have to do, you type rate and replace x with number, for instance 0.1, and then when you type enter, you will get if you put input 0.1, you will get the output is 1.069. So that's how subroutine works, okay? So it won't be executed as it is. We will continue our exercise. So we need to create subroutine number 2. This is Simpson program. In this case, as you see here, the input of the second program is x final. What is the final conversion that you want to have? And then as a result, you will get the integration results. That's the output of integration. So I will construct subroutine number 2, okay? This is subroutine number 2. I put enter. Again, we put def to define function. I call this function as Simpson, and as you see, it receives the final conversions. I call it xb. So once you receive what is the final conversion, so you need to create a new vector of x. That is np.linspace. This is equal spacing, and you want to divide into a number of segment. So that's basically linspace. The beginning is xb and the final is xa. The beginning is xa, the final is xb, and then you want to divide it into a number of segments. In this case is n in plus 1. So why this is n integral plus 1? Because as you see here from previous one, the number of points, if you put n is equal to 10 for instance, so 0, 1, 2, 3, 4, 5 up to 10, and the number of points is basically 11. So it's, in other words, divide from 0 to x into 11 points for instance. So that's why we put n in plus 1. So once you get x, you can define the dx, the spacing. So that's it can be written as xb minus xa. It should be divided by n integral, the number of integration step. Okay, we will create a new vector or new variables. Usually when you have a variable that is output of a calculation, we need to do something called pre-allocation. We provide the place for them. So f is np.0, we call it f for instance, and the size of f is the same as the length of x. And similarly, we can Control C, Control V, fsim. So again, I make a comment here. This is pre-allocate or pre-allocation f. Basically, if you have np.zeros 3 for instance, so it is just an array consisting of 0 with the size of 3, 0, 0, 0 here. Okay, once we finish with pro allocation, we start making a for loop. Why we need for loop? Because we perform this multiplication for this evaluation for all points in range 0 up to n ent plus 1. Why we put an in plus 1? Because we would like to evaluate up to n. If you remember, in for loop, it includes the first number here, 0, but then it excludes the final value here. It means that you expect to evaluate up to 88 here. You need to provide up to 89 because it will stop in 88. So that's why we put it n in plus 1. Okay, and then what happened when you already have for loop? You evaluate the function at all position. That's x, I. And then if you run this program right now, yes, so we will have f. We'll see if we have f here. No, it doesn't show up. The f value will grow, and then we start making we have to print f, or just to see how the f looks like. No, it doesn't show up. Okay, it's not that important. I mean, the f here, it will evaluate for all values in all position, in all points. And now we would like to change the value in odd number and even number. So if I is equal to 0, so then we don't need to do anything, that fsim I, that's equal to fi, okay? And similarly, elif okay, to put it down here. So elif I is equal to nent, this is the final point there. Then it's the same. The fsim I is equal to fi. And then for odd number like 1, 3, 5, and so on. Oops, there's typo here. fsim I is equal to fi. And then elif if it is odd number, is we can say -1 to the power of I, it should be less than 0. So then for this is for odd position or odd number, we can say fsim I is equal to 4 multiplied by fi. Okay, and then for even number, we can say else fsim I is equal to 2 multiplied by fi. This is for even number. And what happened then, when you are done with that for loop, you can calculate the integration result. So the indentation is the same like in for loop, which means that after you finish the for loop, you can have results that is equal to ca0 multiply by u multiply y with dx divided by 3 multiply with the sum of fsim. It means that you collect all the value that you have, and then the integration results, we can say return result. Okay, that's basically for part number 2, where we define what is the x final, we call it xb, and then we give the integration results. So for main program, if you look at, if you want to check what is the value here, if you check z is equal to Simpson, let's say the final conversion is 0.9, then what happened here, and then if you evaluate, you can print z, see if you get number. Okay, as you see here, it works quite nicely. When you put your conversion target is 0.9, you will get the height is 2.66. The thing is, the target is not only 0.9, but we have 21 number. That's our target. So it should move from 0 to 0.9 for various value of final conversions. So to do this, we need again for loop. So we define again pre-allocation first. Z is equal to np dot zeros. The length is it should be the same as nz because nz is 21. Yes. And then the final conversions, we call it x final, is basically we can check here, it's np.lin space. We want to have conversion from 0 to 0.9, okay? And we want to divide it into nz segment. So we want to have 21 point there. So this is the x final that we would like to have. We have 21 here. So z is equal to np.zeros. Again, this is what we call as pre-allocation of z. And then after that, we create a for loop for e in range of 0 to nz, which means that this is from 0 up to 21. But again, 21 will not be evaluated because the final value here is up to 20 to give 21 results. So that's rather confusing actually, but let's see how it works. It's not that difficult actually. Zi Simpson. So now this is for loop and I will grow from 0 to nz minus 1. So what happened if you want to do xf now, we define x final e. So we want to access the x final at element number I. And then zi is Simpson xf now. This is just for pedagogical reasons that I put xf now. Okay, once we have the results, we print. So we call it as like this. We make a height that should be in meters, and then we put vertical line again. This is conversion in percent, I guess. Oops, sorry. This is, it should be the header of the table. I can Control X. So because we want to print, we need to make a header of table. We can print something like this. This is just presenting result. Let's say like this, just a bunch of line there. Okay, now inside this we need to print the z, and it should be a floating number. I can say just 0.2 float. See how it works. And then this is percent 0.2 float. Okay, and then the value is, you need to print z I and then xf now, and then you multiply with 100. Okay, we'll see how it looks like. We clear this one first. Clear, and you check if you get any number out of this. I think we need to put apostrophe there. All right, see how it works. Yeah, we get the result here. You see, we need a height conversion. Oh, okay. We need to make this more vertical. Maybe it's better if you put more space after F. See how it works. All right. It doesn't matter really. I mean, this is just making a table. It's not essential to influence our calculation. Okay, now once we have the result, give some space there. Perhaps it's better this one. You want to make a straight line there. Okay, I think this is an issue with the formatting number. You can put 8 and then 7 spacing there. So it looks better now, as you see there. So we get the conversion and height of the reactor nicer. So the height, I can make it a little bit wider there. See, this is the height and then conversion. Look, 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 look. And then you can end the table by printing a line. This is a bunch of line. And then you multiply by 25, let's say, something like that. Okay, so this is the final results of our simulation. In order to get, let's say, for instance, 40% of conversion, you need to get the height of 0.7. And then for 90% conversions, you need 2.66 meters. And we can also prepare this in a plot because we already have imported the library. We can put plt.plot, and then the x-axis is z, and then the y-axis, because we already have z here, right? We check we have z here, the x final. We can take x final as the y-axis, and then we can put a symbol of red, and then marker size. See, maybe it is clear this way. Marker size equal to 410, and then plt dot grid. We need to provide a grid just to make it nice. plt.x label, you can call it as reactor height. Reactor height should be in meters. And then plt.y label, it is conversion. Conversion is in percent. See, we check how it looks like. Yeah, we get nice plot here showing the relationship between conversion and reactor height. So that's all from me for this exercise, numerical integration. So if I could repeat briefly here, we need to provide what is the data, and then what's the subroutine to calculate function. This is part number 3. And then part number 2 is the subroutine, which define what is the Simpson algorithm. We need to provide the x final. We call it Simpson xf now, but it is received as xb. When you send xf now, it is received as xb, and then you will evaluate this function all the way until you get results. And once you get the results, it should be placed in z at element number I. And then after this, you print the table, and then you can make a nice plot showing the relationship between conversion and the reactor height. So that's all from today's exercise. Thank you for watching. Bye bye.